All right, the last thing we want to talk about in terms of axiomatic semantics is how to use them in a different way. So we've seen several videos of trying to use axiomatic semantics to prove a property of an existing program. And it was a bit of a slog, right? It's quite a bit of work to do this. Our GCD program was pretty straightforward, but generating this proof was not really that easy. We had to do a fair amount of work. None of it was terribly difficult, but there was just a lot to keep track of. And frankly, it's something that might be better done by a computer than humans, and that's why there's been a lot of work in automatic verification of programs. Is there some way we could automatically automatically apply some of those rules? We're going to take a different tack now and see if we can use axiomatic semantics as a way to help us design correct programs from the beginning. Right? So instead of proving them correct, we're going to use these ideas and simply try and write correct programs. Right? So if we think about that GCD program, one thing we might do is say, well, what was our big strategy? What was the high-level design of that algorithm? And from that, consider what a postcondition would be and a loop invariant would be. Right? So in this case, we're trying to design that program from scratch, assuming it doesn't yet exist. Right? And so the big idea there was simply that we're going to compute the GCD by counting down from some value that we knew was bigger than the greatest common divisor, right? And we kept counting down one by one. As soon as we got to a common divisor, then we knew that we had the greatest one. Right? So that was our general strategy, right? Our postcondition, right, was that we wanted I to be equal to the GCD of m and n, right? And maybe m0 and n0, right? Those initial inputs. That was our postcondition. And we wanted to think about a loop invariant. Right? So all right, if we're going to count down, what is it that we want to be true before the loop begins and after the loop? Every single time we take a step, this invariant still holds, so that when we get to the end of the program, we want to make sure that this loop invariant and not the condition on the loop implies our postcondition. Right? That's what we know. After the loop is done, the loop invariant holds, the condition on the while loop is false, and hopefully that tells us something about the postcondition. And that's exactly what we have here. Right? So our loop invariant was for all j greater than I, we wanted to say that j was not a common divisor, right? So we wrote this as n mod j is not equal to 0, and also m mod j is not equal to 0. So it's just telling us that j is not a common divisor. Right? Oh, and this was an or, sorry. So this just tells us that j is not a common divisor. And so we then know when we're finished that I is a common divisor. That's the negation of our condition, right? So that our condition was I is a common divisor. We can go look that up again. That's exactly the condition we had before. And so now it's quite clear that the loop invariant holds and the condition is false. That implies that our postcondition is true. And so this is a way to think about designing programs. So let's give this a try with a different GCD program. Right? So this is an algorithm that will make use of a different insight. Right? And that's shown here in the slide for this exercise, that when we're trying to compute the greatest common divisor of n and m, we can think of decrementing n by the value of m when n is greater than m, right? And those GCD values are the same. Alternatively, we could decrement the m value if it was the bigger one. And the last one, right, which starts to look like the base condition, right, tells us that the GCD of two numbers, n and m, is those numbers if they're the same. Right? So if m equals n, then the GCD of m and n is just m. So what could we think about designing this program? Right? So what would our high-level strategy be here? Right? You can imagine some while loop where there's a if-then-else inside of it, and that if-then-else is going to encode these actions, right? That if n is bigger than m, then maybe we decrement n by m. And if m is the bigger one, then we subtract n from m. Right? And we want to keep doing this until these values are equal. Right? So if we thought about this in a principled way, right, we would want to see that somehow our post condition is going to be, we need to discover the GCD, right? So the GCD of our inputs should be equal to the GCD of m and n, and it should be the case that m is equal to n when we're done, and thus GCD of m and n equals m, or n. Right? So we're keeping m0 and n0 constant, they don't change. We keep decrementing m and n until they're equal, and that should get us to our answer. Right? So in this case, we think, what is our loop invariant? Well, our loop invariant might be that the greatest common divisor of our inputs is equal to the greatest common divisor of m and n, the values that are being updated inside of that while loop. Right, and thus we think that the condition on our while loop, right, we want to keep decrementing these while m is not equal to n. Right? So what you should do is create this alternative GCD program following these steps, right? Figuring out what is the body of the while loop that maintains this loop invariant, right? So what we're doing is trying to start from the loop invariant and generate or write the while loop such that it maintains that loop invariant. We're not starting with code, we're starting with the loop invariant. Alright, so what I recommend you do, oops, I guess I skipped past this initial slide when we started here, is take a look at John Bentley's paper, Writing Correct Programs. So he has an interesting story at the beginning of that paper about a binary search algorithm and how he asked several professional programmers to write the binary search algorithm, and quite a few of them get it wrong. And it's an interesting question as to why that is. So take a look at that paper. It explores these ideas of program development using loop invariance, which is sort of the key piece in axiomatic semantics. And then finish off this exercise to create this GCD program that's based on a different strategy than the one that we proved correct before. All right, so what we see then is that the axiomatic semantics gives us sort of a disciplined way to create programs. We shouldn't sit at our keyboard pounding away at characters hoping to create the right program. We really want to step back and figure out what is it that we're trying to do. And a great way to make a plan for writing code is to come up with the loop invariant. Right? If you can't come up with the loop invariant, you're probably not ready to write the program. Even if you can't precisely state the loop invariant, you should have a good intuition about what that loop invariant is going to be. All right, so give that exercise a try, and we'll pick things up after this. Actually, I think this is the last video. Yeah, sorry, this is the last video for the axiomatic semantics material.